Hi, everyone, and welcome to Exploring Exoplanets with the Bell Museum. My name is Mila Velimirovich Holtz. I know it's a long name. You can just call me Miss B. And I'm going to be your instructor for this lesson. This video will include some information about exoplanets along with some activities that you can do with us if you would like. Now, if you need to, you can pause, rewind, or fast forward the video as much as you need to. There are also some materials you can either use with us as we go through the video, or if you must, you can stop the video and take a look at our webpage. During this video, we are going to learn about what is an exoplanet, how can we find them, and why should we even be looking for them. Not only that, but we are going to learn how we can filter a necessary item for survival while traveling through space and home as well. I'm sure most of you have heard the term planet before. In fact, we live on a planet ourselves, Earth. There's actually a few planets in our own solar system, including, but not limited to, Jupiter, Mars. Oh, wait. I'm not here to talk about the planets in our solar system. I'm actually here to talk about exoplanets. An exoplanet is like a planet we have in our solar system, except for one big difference. Anyone have a guess on what that might be? All right, I'll give you a clue. The term exo refers to outside. Any ideas now? Do you give up? That's all right. An exoplanet is any planet outside of our solar system. The actual first discovery of an exoplanet was in 1989. That was before I was born. This planet is referred to as Gamma Cephei AB. This and many other discoveries helped to spur on the research of exoplanets. And at the moment, we have 3,200 confirmed exoplanets. That might seem like a lot to you, but in fact, there is 5,600 more possible exoplanets out there. And that's only what we think. There could be so many more than we've actually found. Well, let's learn a little bit more about exoplanets by watching this short video.
An exoplanet is a planet outside our solar system orbiting another star. They are also called extrasolar planets, and thousands of possible exoplanets have been found using ground-based and space-based telescopes. There are different types of exoplanets: the gas and ice giants. These exoplanets are similar to Jupiter, Saturn, Uranus, and Neptune. Around two-thirds of exoplanets that have been discovered are either gas or ice giants. Hot Jupiters, which are planets similar to the mass of Jupiter but orbit very close to their parent star. Super Earths, rocky planets with up to 10 times the mass of Earth. Pulsar planets, planets that orbit pulsars and neutron stars. Chthonian planets, planets that were once gas giants whose atmosphere has been roasted away because it moved too close to their parent star. And exo-Earths, planets that have similar mass, composition, radius, and atmosphere to Earth and orbits the habitable zone of its parent star. The habitable zone is the range of distances from a star where liquid water can exist on the surface of a planet. This range depends on the size and the temperature of the star. The TRAPPIST-1 planetary system is composed of 7 planets, of which 5 are similar to size to Earth and 2 are between the size of Mars and Earth. 3 of the planets orbit within the habitable zone. All 7 planets orbit much closer than Mercury orbits the Sun, and the planets pass close to one another that the planets appear in each other's skies. The TRAPPIST-1 is an ultra-cool red dwarf star, slightly larger but much more massive than the planet Jupiter. Its planetary system is 39.6 light-years from the Sun. Thousands of planets around red dwarfs have been discovered by the Kepler Space Telescope, and some planets orbit a binary, triple, and even a quadruple system like Kepler-64. About 1 in 5 Sun-like stars have an Earth-sized planet in the habitable zone. Considering that there are over 400 billion stars in the Milky Way galaxy, there is a big possibility that the Milky Way contains billions of other worlds similar to our own.
right, so we've learned a little bit about exoplanets. Big question. How do we find them? Currently, scientists are using 5 ways to study them. Number 1 is called the transit method, which uses the change of the star's light to detect an orbiting planet. In other words, when we see the star, if there's at any time the amount of light changes, we measure it to see if it's consistent and if there possibly might be a planet orbiting that star. Number 2 is called radial velocity. It's when scientists look at the star's wobble. Number 3, microlensing. This explores the bending of a star's light from the gravity of a passing planet. Yes, everyone, light can be bent by gravity. Isn't that crazy? Number 4 is imaging. This one's kind of tough. What scientists have to do is they actually have to block the light of that star and try to see if there's any light reflecting on nearby objects, like a planet. Finally, we got our last method, which is astrometry. And this one looks at tiny changes in the interactions between different stars. Now, if you'd like more information about how these all work, no worries. We're going to watch a little video about these 5 different methods.
As of last year, from a statistical standpoint, we now know that there are 1 to 3 Earth-sized planets or smaller around each and every star in the galaxy. The next time you go outside and look up at the night sky, just pick a random star.
Planet.
Yeah,
2 of them.
Probably 5.
Yeah.
5 planets, one of them sitting in the habitable zone.
Okay, well, so this is just a table of the 5 sort of most prominent exoplanet detection techniques.
The way we discovered the first planet outside of our solar system was using a technique that we call the Doppler technique, or radial velocities.
They measured the velocity of the star as a function of time. And here's 0, and there are plenty of stars that just look like this. They're moving away from us, but at a constant rate. So it's probably nothing there. But if you see a star with the velocity, it's changing and it maps out a nice sine curve.
And then you ask the question, well, what do you know about physics that could possibly be making it move? Well, something must be tugging it.
It's the same way that you can tell how fast the car is moving or a train by its sound.
The faster the star is moving towards you, the closer together the wavefronts would be, and the higher frequency or the bluer the light would appear. And then the faster it's moving away from you, the redder it appears. You have your sun, and then orbiting around it is a planet. And when the planet is over here, because of gravity, the planet gets tugged inwards, but also it tugs the star ever so slightly inwards. And then when it orbits here, the star gets tugged over here, and same thing, same thing.
The period of this is 1 orbit, and the amplitude, how big it is, depends on the mass of the planet.
Which is why the first thing that we saw was...
They're called hot Jupiters.
Because astronomers are very clever with our naming.
Right, yeah.
What we're actually observing is the spectrum of the star.
But seeing the whole curve is really hard to measure.
It'd be this featureless thing with nothing to grab onto. All these lines give us a handle to measure the velocity of the star. Every single atomic and molecular transition happening in the star is moving, getting Doppler shifted in the exact same way. So every single line has a story to tell about the motion of the star.
And right now we can do like 1 meter per second, which is walking speed, which is really slow. That's 100 light years away. The shifts that we're talking about for these planets are extremely small.
We're sampling this with a little CCD detector like the one in your camera phone. So we're watching the line shift by about 100th of a pixel, which is about the same size of 80 silicon atoms lined up end to end.
That's crazy.
Yes, we are living in the future.
So the analogy there is that you're standing right next to the world's brightest lighthouse, and you flick a lighter on. The act of seeing planets is analogous to being able to discern that flame next to this lighthouse when this lighthouse is in California and you're standing in Hawaii. That's the scale of the problem.
And the only reason why we can even do it now, today, is because you have these crazy adaptive optics technique, and this allows you to take away the blur of the atmosphere. And with that, we've been able to see exactly 4 other planets.
HR 8799B, C, D, and E.
And then there's like light curves or searching for planets that transit. What we do is, again, we point our telescope at a whole bunch of stars and we just track how much light we can see from them. And if we're staring directly face on and then you have a planet and it goes in front of the star, the light from the star goes down, so you just see a constant dip, and then it leaves the star and slowly goes back up. You try to find dips, periodic dips in light.
You have a big planet and a small star, look how deep that goes. There's a tiny planet, that little dot right there, causing this tiny little dip in light. Then you have kind of intermediate to both cases.
You have to be so precise you can see 1,000 difference.
So Kepler was launched 3.5 years ago.
And every 30 minutes, it takes a measurement of the brightnesses of 160,000 stars.
So you have to look at a lot of them because just geometrically, the planet has to pass between you and the star. So Kepler has found about 2,500 what they call candidate planets. So we talked about transits here. And we have a star with a planet going around it. The planet has a very regular orbit. So now let's say we have a second planet in here.
So the outer planet can tug on the inner planet and cause it to arrive late to its transit. And then a little bit later, it's ahead of it and it pulls it forward and it causes it to arrive early for its transit.
So you actually see a nonlinear period.
Then you can say beyond any reasonable doubt.
You have two planets here. So
If you want to really get down to magic, then you really have to get into relativity. Let's say we're standing over here and we're looking at a star here, far away from us, all right? And then let's say that there's light from another star way back over here. The photons that travel from this star, when they get into the gravitational field of this star, it actually gets bent by the gravity of that star, because anything with mass bends space and time, and it actually acts as a lens, so it's called microlensing. So people were doing that for a while, and then one day they got a secondary blip, and that's because this guy brought a buddy with him. He had a planet, and this lensed light got lensed again.
Double lens.
When the planet was drifting by as well. One of my colleagues who does the Doppler technique so she raises her hand in the middle of the talk. She's like, let me get this straight. You are measuring planets that you never see around stars that you never see. Is that right? It's basically what you're doing.
So the thing is, in 20 years, the consciousness of humanity went from, gosh, I wish there's got to be like some planets out there, right? 20 years ago, right? To now, so there are literally billions, maybe trillions, of planets in our galaxy.
And that's just our galaxy.
yeah, the same number of stars that there are in our galaxy is the same number of galaxies in the universe.
Roughly, yes.
So there's a billion times a billion planets,
Yeah.
conservatively speaking.
And once
Nearby.
you start seeing all these planets and how they're arranged, then that starts to give you insight into how they could have formed, how the whole system evolved over the lifetime of that
In fact,
system.
now you're basically connecting those diffuse blobs of gas and dust out there
And how
to
they
living
connect.
beings.
Yeah.
That's what we're doing here. We're getting not only just finding planets, which is amazing in and of itself, but we're basically tracing our past as humans back through the cosmos, going from where we are right now back to those dust lanes. And we're doing so by looking for little blips in the light from stars. We're looking for little wobbles in the stars caused by the gravitational tug of a planet. We're doing it through general relativity. We're taking pictures of planets. All of that in and of itself would be cool. But it goes so far beyond that. But we're revising our own origin story.
All right, well, so far, most exoplanets have been found by using the transit method. How about we try and see if we can discover our own exoplanet? All right, here we have an image of a planet orbiting a star right in front of us. On the left-hand side, there is a little graph. Now, this graph is very important for studying the transit method, and I'll show you why in just a moment. So again, keep your eyes on this area right here with the left side. So this line right here is indicating the amount of light the star is giving off. Whenever a planet or an object goes in front of it, boop, it dips. The reason for that is that here, we're seeing less light because that planet or object is blocking the star's light. Again, let's take a look. We've got that stray amount of light that we're seeing, and we keep seeing it. As you notice, this planet is going to pass, and boom, we start losing the light. As soon as the planet leaves, the light comes back up. Now, scientists use tools to measure the output of the star and record all these dips. In fact, they look for at least 3 dips with even spacing before they can possibly confirm an exoplanet. Do y'all have an idea why they need to find 3 dips? No? That's all right. It can be hard to think of because we don't really think of stuff flying in space. But the fact is, if there's only 1 dip, it could mean that it's not a planet. It could just be some space debris flying around, like an comet or even a spaceship. Yikes. So 3 dips indicate most likely that is a planet that's orbiting. 1 dip means it orbited once. 2 dips, second orbit. 3 dips means it went around a 3rd time. Of course, scientists want to see as many dips as possible, but 3 is usually an indicator that let's keep looking and see if we can actually find an exoplanet. Well, let's move on to your challenge. Here's your challenge. I'm going to show you 3 graphs. Only one has an exoplanet orbiting it. I want to see if you can figure it out which one it is. Now, as a helpful hint, stars never give off a perfectly straight line of light. Most of the time it's wavy, and that's because they're stars. Sometimes they give off more light and sometimes they give off less light. It just depends. Solar flares and all those kind of things. So just be aware that sometimes the graphs can be a little bit wiggly or they can go down and up. But again, you're just going to be looking for those little dips down that indicate something is blocking that star's light. All right, let's begin this challenge. I'm going to show you your first graph. This is graph A. Again, look carefully at the graph. Look at the light curve and see if you can find any dips that might indicate a planet that is blocking the light. If you need more time, feel free to take a picture of the graph with your phone or take a screenshot of the graph. But we're going to keep moving. Graph B. Again, look carefully at that graph. Look at the light curve and look at the dips. Does it seem that there might be a planet orbiting this star? Again, if you need more time, feel free to take a picture of the graph with your phone or take a screenshot. Final graph. Graph C. Again, look carefully at the light curve and try to see if there are any dips that could indicate a planet. Again, if you need more time, feel free to take a picture of the graph with your cell phone or do a screenshot with your computer. Now, I am not going to tell you the answer right now, but I will tell you at the end of this video. So if you'd like, you can stay with us and find out, or you can just scroll all the way to the end. Totally up to you. But I'm going to keep going. Now, you might be curious about what scientists are looking for when they search for planets. The big thing that they're looking for is an exoplanet that is habitable, or in other words, a planet that can have life. Scientists look for one of 3 things when searching for life. Number 1, what kind of light spectrum is that planet giving off? Now, we see different colors of lights given off by planets. And at times, when we look at a planet, we don't see all the colors. In fact, there's usually a space in between some of the colors. So if you take a look at this picture under the light spectrum, above is an image of Earth and what it would look like if we were looking at the light spectrum of Earth. If you notice, There is a lot of little holes in our light spectrum. These holes indicate certain types of gas. So, for example, this opening here would indicate that we have methane gas in our atmosphere, which is true. We also have CO2, water, oxygen, and ozone. So when scientists are looking at different exoplanets, they take a look at this light spectrum and see, are there any openings? And where are those openings? Usually scientists hope for openings that indicate water vapor or oxygen. Number 2 is the type of star, which is very important. You see, big, bright stars burn out quickly, which means it'd be very difficult for any life to form on a planet near this star. Usually, scientists look for stars that are very similar to our own sun or are light dwarf stars, because these are good indicators of condition of life on planets nearby. Number 3, the habitable zone. This might sound weird to you, but it's actually a very simple idea. The habitable zone is the area where a planet is located that is not too hot or too cold. In other words, you do not want to be a planet right next to your star, or else it's going to be way too hot. But you also don't want to be a planet too far away from your star, because then it's going to get chilly and a little bit too cold. After all, no one is going to want to live somewhere where it feels like the inside of a volcano or everything is frozen solid. Well, to be fair, at least not humans. The other very important thing about living in a habitable zone for a planet is that it is a good indicator that there is water. And based on what we've seen, life needs water, or so we think. See, water is where life begins, and it also is a major component of survival on Earth. Not only that, but it's a good indicator of a habitable planet for ourselves. This means that we have a potential of living there ourselves. However, even if we could live on that planet, it wouldn't mean we could just go up and drink the water. We would need to filter it, just like we have to filter water on our own planet. Which leads to our next activity challenge. As you recall, we all need water to survive, whether that means we take water from exoplanets or water from our own planet. Before we even think of drinking the water, we need to filter it. So how about we learn how to make our very own filtration system from items you can find outside and around your home? Now, before we start, I want to say one thing. Do not drink your filtered water. Though you may have cleaned the water quite a bit, there are still a lot more filtration steps that will need to be done to be able to drink water. This is just an experiment to see how clean you can get your water to get, not to drink it. If you'd like to learn a little bit more about how water gets cleaned in your area, visit your water treatment plant's website. Now, on to the experiment. For this experiment, you are going to need a glass jar or clear cup or a skinny clear container, a bowl / old container, some muddy water that contains, obviously, water, some dirt, pieces of grass. Sand is optional. but it does add an extra challenge. You'll need a funnel or a water bottle you cut in half, and then some filtration materials. You can use any of the materials listed below or any materials you can think of. Some materials we have talked about would be coffee filter, gauze, cotton balls, sand, small rocks, pebbles, aquarium gravel, charcoal, a lot more things. For my experiment, what I've done is I've used pebbles, a coffee filter, and sand, and tape. All right, let me show you what I made. So first off, when you start this experiment, you're going to need to make some real gross water. I'll show you the example that I've made. This is water that's mixed with sand, dirt, and some grass that I found outside. I just mixed it up in a plastic Tupperware container that I'm never going to use again. And this will be the water that I need to filter. Yuck. As for where I'm going to be placing my water, I'm planning on using this big mason jar. But again, you can use any clear container. You do want it to be relatively clear so that you can see what your water looks like. As for my filtration device, what I used is a plastic bottle that I cut in half. Now, one thing I will tell you when you're cutting in half a plastic bottle is that you're going to want to turn it on its side and pinch it together as much as possible when you use the scissors. And be very careful. You do not want to force it. Take your time. I also included on the very top some tape. When you cut your bottle, there will most likely be some sharp edges. You want to make sure you don't cut yourself while filtering your water. So use some tape. I just use plain old Scotch tape to cover it up. If you want to go more fancy and do some colorful duct tape, do that as well. Again, the purpose of the tape is just to protect you from getting cut from the top. In my filter, I've used 3 things: coffee filters, sand, and pebbles. Now you'll notice that I have my coffee filter on the outside. When I first built this, I actually put my filter on the inside. Problem was that when I poured my sand in, it just came through the bottom of my bottle. Now, if you can find a better way to get a filter inside, or maybe use some cotton balls or gauze, you might not have to do this, but I had to tape a coffee filter on the outside to help prevent any sand from coming out. All right, once you've made your layers of filtration items, take your water. Now, one thing I'll point out real quick is that I have left space on the top. You're going to want to do that as well. You do not want your layers to go all the way up into your bottle. Make sure, again, that you use at least a little bit of opening so that the water can get in. All right, let's pour our water into our filtration device and see what happens. All right, I have my water in. You can see what it looks like. Kind of looks like lake water. Kind of gross. That's why you shouldn't drink lake water, just FYI. And now my water is coming out at the bottom. Now this could take some time. You have to remember that your water is now draining through a lot of different layers. And if you have more layers than myself, it's going to take a while. But that's okay. Sometimes the longer it takes might be a good indicator at how good your filter is doing. But if we take a careful look right now, this is what my water looked like before. And as it's starting to fill up, you can definitely see that it has cleared up quite a bit. Now, I only use 3 things for my water filter. You can use more or less. And maybe you can think of a better design than the layers I have created. What I did was coffee filter, sand, pebbles. Maybe you want to change it. Maybe it'd be pebbles, sand, coffee filter. But big suggestion is that you use some type of coffee, gauze, or cotton balls on the bottom part of your filter. Therefore, no sand will get out like mine did. All right. If you'd like to, right now, try to build your filter and create some dirty water to filter as well. Or you can keep watching to see what more we have to give you for the rest of our video. All right, so we put aside our little experiment, and we're going to continue learning about exoplanets. The remainder of this time is going to be looking at why we study exoplanets. What's the point? Why are we so curious about them? Well, there's actually a lot of reasons for why exoplanets could help us out in the future. For one, they give us a lot of information on our own solar system. They provide us information related to the past of our solar system, the present of our solar system, and the future. Another reason is to find life on other planets. Could there be life out there? And we're not just talking about those little green aliens, though that would be really cool to see one. Most scientists are actually just looking for any form of life, including teeny tiny cell to one organisms. Scientists are also looking for exoplanets that could be potential homes for us in the future. So we need to find habitable exoplanets, which brings us to our final exoplanet challenge. There are a lot of interesting exoplanets out there, but which one do we visit? That's what I'm going to have you decide. For your next challenge, you are going to make an exoplanet brochure. And you are going to need to convince us that your exoplanet is the best place to be. Now, before you start, some very good resources for you to help you create your exoplanet brochure are the following. Number one is NASA's Exoplanet Travel Bureau. This is a website created by NASA that shows some different exoplanets and what they believe the future exploration of that exoplanet could be. They have a lot of cool simulations that you can be a part of, and also some cool posters that you can take a look at. Also, NASA's Galaxy of Horrors shows some alien worlds that you can look at that might have some scary beings living on them, as well as the universe of monsters, which is also an idea of what those alien worlds might have living on their land or water. Now let's get started. What's great about this challenge is you really do not need much. If you want to make a giant brochure from a poster board, go to it. If you prefer just to make a small one on some notebook paper, that's good too. It's all up to you. Feel free to use paints, markers, pastels, whatever you want. But there are a few limitations that you need to follow. First off, you need to pick an exoplanet, just one, and maybe try to pick one that no one has tried to make a fun little brochure for. Try to figure out what makes that exoplanet unique and interesting to see. After you've gotten your first topic or fact, make a fun catchphrase, like NASA, who came up with lava life for Cancri E exoplanet. And the reason they called it that is because it is believed to be covered in lava. After you've come up with your fun catchphrase, create an image of the planet that makes it unique. You can create machinery, robots, or even homes that you might have people use while they explore the planet or live on the planet. Then just make your brochure. Use whatever crafting materials you want. If you're not much of a drawer, like myself, maybe think about using old magazines or pictures. Let me show you one that I made. And again, as a reminder, I am no artist. All right, everyone. So for my project and for my exoplanet, I chose Kepler 452b. And what I decided to show off is that it is in the habitable zone, which is just right. It is not too hot and it's not too cold. It is just perfect. A perfect home away from home for those of you who want to leave our solar system. And again, not an artist, but I'm still quite impressed that I was able to pull it off. Now, if you found this video and activities interesting, and now maybe you're starting to think that you want to study exoplanets in the future, one great place to study exoplanets and other interesting phenomenon is Minnesota Institute of Astrophysics at the University of Minnesota. Their main research is on astrophysics and using technology to study outer space. If you want to learn more about their program and how you can get involved in the future, take a look at their website and see what cool projects they're working on right now. Well, that is the end of our video, and as I promised, I am going to give you the answer to the graphs. Drum roll, please. The graph with the exoplanet is graph C. Now, the reason we know that there could be an exoplanet there is if you look at our light curve, there are consistent tips in the same location around the same amount of time. And there's a lot of them, not just 3, but multiples, which to scientists could mean there's a good chance that there is a planet that's orbiting this star. If you're able to figure it out, congrats. And if you weren't, no big surprise there. I didn't get it the first time I saw it. So it just takes a lot of practice before you can discover exoplanets. Well, everyone, we learned quite a lot today. We were able to define exoplanets and figure out how to find them. We learned why scientists are even looking for them. And then we learned how to filter water by creating our own filtration system that we can potentially use in our travels through the exoplanets. It's been one busy day, and the Bell Museum would like to thank you so much for watching this video and trying out some of the activities that it provides. We hope to see you again soon. Keep exploring, scientists.